integral of
ln x over x.
dx. Okay? So, when you look at one like this, and it's not a basic, it's not one of our basic page 333 antiderivatives that we have to know, right? That we just have to memorize here. And so the only other thing we know is u substitution. I mean, let's think about it. We got basic antiderivatives, like I gave you that one yesterday, whereas 3 e to the x minus sine 3x plus x to the fourth. Just some basic antiderivative ones. If it's not that, then it's going to be u substitution. On the gateway test, I would say you're probably going to have maybe one or two that would be maybe some basic antiderivatives. You might have to kick out an inside or something like that. And then probably 5 or 6 of them are going to be u substitution. Probably the vast majority of u substitution. That's the main technique we have. Now today we're going to learn one other technique that you need when u substitution doesn't work. There are a number of techniques for doing antiderivatives. Notice I don't call them rules, but they're techniques. We have derivative rules. If the function looks like this, you do this. If it's a product, if it's a quotient, if it's tangent, if it's whatever, this is the rule for doing the derivative. When you're doing it backwards, remember I said that the book says it's more art than science, right? So we have techniques. If it looks a certain way, if it has a certain characteristic, then we might want to try this technique to get the antiderivative. Or maybe this technique works. Or maybe it's a combination of a couple of techniques, right? Well, we're only going to do 2. We're going to do u substitution, and then which is basically the chain rule, the inside stuff in reverse. And then we're going to do this integration by parts, it's called, which is the product rule, kind of in reverse. There are a bunch of other ones that when you get into Calc 2, you will do those. We're not going to get into those. So it's going to be one of those situations, right? It's going to be a basic antiderivative, probably a few of those. Most of them will be u substitution, and then there'll be a few of this other technique we're going to learn today. Okay? All right, anyway, we want to pick a u. Now, usually we pick what? No.
The inside.
I don't mean in this problem. Usually we pick something on the inside. Well, there really isn't anything on the inside. Another thing we've done is let u be the bottom, right? That's happened on a few problems. Let u be the bottom. And that's really not going to work here. Matter of fact, never, ever, ever in u substitution would you ever let u equal x. Because there's no point. Because the du would be dx, and then in this problem you'd end up with ln u over u du, and what did you accomplish? Nothing. You've got the same integral just with a different letter. So we would never, ever, ever let u equal x in u substitution. Now in the new technique we do, it actually ends up happening. But in u substitution it would do you no good to do that. So you don't really have many options other than to let u equal what? Natural log. But then the other thing I said yesterday you should be thinking about when you pick a u is what's the du? And we want that to be setting there in the problem. Well, if you let u equal ln x, what's the du, of course, which means the derivative? 1 over x dx, which voila is setting right there. 1 over x dx is there. Okay? So that's why we want to pick u to be ln x. So the du is 1 over x dx, which is nicely setting right there. So my new integral, the top would just be u. The 1 over x dx is just du. So the whole thing just simplifies to that. Okay? Now the whole point of u substitution is turning our integral, which is something we can't do, something we don't know how to do the antiderivative of, turning it into an integral that we can do, where we can do the antiderivative. So this is just a power rule, so that'd be 1/2 u squared plus c. Jared and I were talking yesterday, you don't have to write this step with the u. If you just know it's going to be 1/2 u squared, and as you write it, you just go ahead and substitute your u in. I'm fine with that. That's okay, right? You don't have to have this step here. Okay, I'm looking for that final answer. Okay, so there it would be. All right. All right, another one.
31.
31. What is it?
Integral x times
the square root of 3 minus 2x. And then times dx.
Okay? All right, like that. So, we said that what we want to pick for you generally is the inside, which is going to be a good one to do here. Now, again, if you're thinking a step ahead, you let u equal 3 minus 2x. So the du is going to be what? Negative 2 dx. Now the negative 2, we don't really care, it's not in there. But is there just a dx there? Well, there is, but you can already see there's going to be an extra x setting there. Whenever you have an extra x, one strategy is solve that equation for x. So is this the one we kind of did? No, that was 28, but this is similar, isn't it?
Yeah.
This is similar. Okay, so the du is going to be negative 2 dx. We don't see a negative 2 in here anywhere that we would use, so we're going to divide it over there. Okay, and we get that. And so now my new integral, this part will just be u to the 1/2. This part, the dx, is just negative 1/2 du. So I'll put the negative 1/2 out here. Put the du. Now I want the du way over there. I always want the du at the far right end. Okay, and I know I've still got this x hanging out here. This is where circling it really comes in useful. So I've taken care of that. I've subbed out that. Now I got to sub out this x. Well, I'm going to need to take this and solve it for x. So I'm going to subtract u. Well, let's see. I'm going to add 2x over there to be better. I don't want that negative messing me up. So I'm going to do this. I'm going to do it this way. So I'm going to add 2x to this side. Subtract u. Again, the way you write these things, I think, can make or break as far as making some mistake. Because remember, in the gateway test, it's right or wrong. You miss a negative or some small thing, you miss it, right? And then we divide by 2. Now, yesterday I told you a good way of doing this instead of dividing by 2 would be to do this. I would write it as 1/2 and then the 3 minus u. So now when I go to put that over, when I sub out this x right here, I'm going to go put that over there. I would put the 1/2 out here and the 3 minus u in here. And then I don't have a whole bunch of messy fractions and stuff in there. Now you can put them in there. I don't care. It doesn't matter. I'm just telling you they get hard to keep track of. And it's a easy way to make mistakes. So this negative 1/4 is going to stay out here. I'm going to distribute this. Now notice I still have my integral symbol, which means I have not done the antiderivative yet. All I'm doing is rewriting it. So this would be 3u to the 1/2 minus u to the 3/2 du. Right? I just distribute, add those powers. Okay? And my fear is for some of you, you're gonna do okay on some of the calculus stuff here, and you're gonna miss some because of fractions, not multiplying fractions correctly, or not adding numbers correctly. And you just got to be real careful with that stuff. Okay, now we're ready to do our antiderivative. So now we raise it like this one. This is going to have a bunch of fractions in it. So we're going to raise this up to what? 3/2 and divide by 3/2, which means times by 2/3. Now, both of these have a negative 1/4 on them, so I'm going to bring that along. So I got my negative 1/4. I divide by 3/2, that'd be 2/3 u to the 3/2. And I forgot this 3 too, didn't I? I got to remember that 3. I'm going to stick that on there also. Okay? And then minus, and now I got this negative 1/4 again. Raise that up to 5/2 and divide by 5/2, which would be 2/5 u to the 5/2 plus c. So now what do I got here? You just multiply across. So that'd be negative 6 over 12. That's negative 1/2. U to the 3/2, I can put my u in now, so that'd be 3 minus 2x to the 3/2. This turns into a plus. What's that? 2/20? That'd be 1/10. U is 3 minus 2x to the 5/2 plus c. Okay? Now, these get hard to check on your calculator. Now, you can look in the back of the book. They may write it a little differently, although I think this one they wrote pretty much like that. Or in my answer book anyway. If you're at home, you don't have that, use a calculator. A lot of you, I noticed, did the odd ones, which is good because you can check them that way. That's good. But remember, you got your calculator too. You can type these into your calculator. Now, remember what we did with derivatives. if the calculator gives you something that looks different than your answer, type your answer in, and a lot of times it'll do it, or put your answer equals their answer, see if it says true. Okay? So that's another way you can check these. All right. Yes?
51.
51.
Integral of tangent x.
Good one. Now, remember I said yesterday that sometimes the antiderivatives that are messy, the integrals that are messy end up being the easiest ones, right? Because derivatives, when you do the whole product rule, quotient rule, they get messy, your answer. Well, when you go in reverse, it should be the other way. It should be messy to start, simple to end. So sometimes the hardest ones to do are the ones that are simple looking. Because there's nothing to grab onto. There's nothing to pick for your U, right? There's just nothing you can do with it. So sometimes those are the hardest ones, and that's where we have these other techniques that come in. But here we actually can do a U substitution. I'll talk about it here in a minute. Now, with that said, we have a list on page 333 of 9 ones you're supposed to memorize. That list could have been long. I mean, the integral of sine is on there. The integral of cosine is on there. We could have put the integral of tangent, just had you memorize it. This book just decided not to, and that's fine. So then you better be able to do it another way, okay, which we can. So one thing, and I'm glad you asked about 51, because if you just go through that first section, if you only went like straight down the page, 23 through 40 or whatever, those were all algebra ones. They all had just a bunch of x's in them. No trig ones or anything like that. And those were later in the later ones. So you want to jump around and get a variety of different problems. Trigs, exponential, stuff like that. Now, since we don't know what tangent is, matter of fact, if you go look at your derivative rules, if you go up and down this list and look at the right-hand side, tangent doesn't show up there anywhere, right? Like this one's on our list. The antiderivative secant squared is tangent, but we don't have the antiderivative of tangent anywhere. It's not on here, okay? Well, here's what you can do on this one, and here's what you do on a lot of triggers. Use a trig identity. Change this into sine over cosine. Okay? There's a lot of different little tricks. This is why practicing is so important. If you did 5 problems for practice, maybe you did good on those 5, but you may not have, and you might think, hey, I got it, this is easy. Well, you may not have run into some of these various situations. So the more practice you do, the better chance you're going to run into these different situations that come up, and then when they come up on the gateway test, you'll recognize it and say, hey, oh yeah, I've seen that. I've seen that. Okay? So this is going to be a U substitution. Why? Well, it's not one of the basic ones we learned, and you don't know any other way to do it besides U substitution. Now, when we learn this third way, then you'll have to figure it out between those. So what could we possibly let U equal here? Well, we have 2 choices, sine or cosine, right? I think it's the bottom one. And here's why. If you let U be sine, what's the du? No. If you let U be sine, the du is cosine x dx. Is there a cosine x dx set in there? No, because it's on the bottom. That's not a cosine x dx. It's a 1 over cosine x dx. So we can't let U be the sine. We have to let U be the cosine. Okay? And because the du of cosine is negative sine x dx, which happens to be setting right there, except for the negative, but we can divide that over. So we can divide the negative over to this side, and there is our sine x dx, which is good. So our new integral is, so Trevor, we were talking about this when I came around. So you understand this part, we're just substituting, right? So this sine x dx is going to get replaced with what? Just the, right here. It's equal to, right, negative du. So that means in my new integral, I need a negative, which I can put here, and the du, of course, always goes at the end, so I put that over there, right? And then this thing is going to get replaced with u, but it's on the bottom, so since I have nothing left on top, I got to put a 1. But look at that. It's one we know. What is the antiderivative of 1 over u? Natural log. Now remember, that's only if it's u to the first. If this was u squared, that wouldn't be ln. That would be a power. That'd be negative 2 power, and we'd go from there. Okay, so ln u, put your bracket or absolute value, plus c. So this would be negative ln. What was u? Cosine? Cosine x plus c And there it is. Some books would probably have you memorize that. Some books would just, they'd have in their list, integral of sine is negative cosine, integral of cosine is sine, and integral of tangent is negative ln cosine x. Sometimes that's written as ln secant, because you can take that negative and put it inside, and you have cosine to the negative 1, which is 1 over secant. So some books put the derivative of antiderivative tangent as ln secant. Okay? Yes, Laura.
So, okay, x is the only thing that you can put into ln. You can't do like 1 plus x squared or something like that. Like if it was
Right, and 1 over x to the first is the only thing that becomes an ln. Now, unless you have an x plus 3 or an x minus 2, just some little shit.
Would that still work?
But that would still work, yeah. Or if you had 2x plus 3, right, that would be an ln.
Okay.
But it's got to be just an x, a linear thing down there at the bottom to do an ln, yes. No other thing would be ln. Yes.
The lower derivative, you can do like a second and third derivative and so on. Is there a second antiderivative for the derivative
Sure,
that you can calculate from like an original like integral?
yeah. But I don't think it's useful for anything. You know what I mean? Because I haven't even really thought of that, but your first derivative is the rate of change of the original, and your second derivative is the rate of change of the rate of change. And so those things kind of physically make some sense, especially the first two. For antiderivative, it's this thing called, it's the area, and so I'm not really sure there's another thing. Unless that maybe gets into 3 dimension. Because I know when you go to Calc 3, but I haven't done anything in Calc 3 for 30 years. So, you know, for a long time. So, you get into double and triple integrals where it has 2 of these signs, which I think probably does have that to it, that capability to it, that second antiderivative kind of thing. All right. Now, by the way, remember we said we could check these, right? So I could do the derivative of this. Think about this. The derivative of this would be negative 1 over cosine times the derivative of the inside. What's the derivative of cosine? Negative sine, and then the c would just go away. The 2 negatives cancel, sine over cosine, which is tan. So it checks. Okay? All right. While we're on that topic, let's just look at 52 real quick, because that just reminded me of that one. 52 is secant tangent dx. What's the antiderivative of secant tangent dx? Can anybody just look at it and tell me? Anybody just tell me what that antiderivative, the answer is? The antiderivative of secant tangent means, is there a function that when you do the derivative would be secant times tangent? Isn't that secant?
Oh, yeah.
That is secant. If you really know your derivative rules, when you see that one, there it is right there. Right? That was one we were supposed to know. Now, we didn't run into it very often, right? So you didn't use it too often. We said we should memorize it, but, you know. So the antiderivative of secant tangent is just secant. Okay? So again, we could have put that on the list. But, you know, we chose not to. So, go ahead and do the same thing on this one. Change secant to 1 over cosine. Change sine to sine over cosine. And you would have sine over cosine squared. Now remember, cosine squared is actually that. Now I'm not going to finish this one, but what would you let the u be in that case? Cosine again, which is the inside. And then the du would be negative sine dx, which is sitting right there. Now this would be one of those, it's not an ln, it's 1 over u squared then, like I was just talking about. This would be 1 over u squared, which is a power rule, not an ln. And then you would go through and you would get it. And sure enough, it'll come out to be 1 over cosine, which is secant, right? And so it will come out to be secant. But it'd have been nice to know. So if this had happened to be on the gateway test, you could do it with the u substitution. That'd be fine. But if you just know what it is, you can just write down the answer. Not have to do it. Okay. What else? Any others?
41.
Any of you thought were kind of strange? 41. What's that one?
X plus 4 over x squared plus 1.
Oh, very good. Now, whenever I see x squared plus 1, I think of 1 plus x squared. Now we would normally, in algebra class, you're always taught to write it in descending order, highest power first. But why would I want to write that 1 plus x squared? What would be the advantage of writing that as 1 plus x squared? It looks like arctangent. It looks like arctangent. Now, you don't have to write it 1 plus u squared. It could be u squared plus 1, right? It doesn't matter. That's how we write it. Now, in arc sine, it does matter. You got minus sign, right, with the square root. But I think anytime you see an integral, an antiderivative, where you've got a 1 plus something squared on the bottom, or a square root with a 1 minus something squared, you better recognize that as arctangent or arc sine, because those are in our list right here, right? Those are down here as ones we have to memorize.
Will arc cosine not be on the
Arc cosine I will put on. All it is a negative, so it's actually the same. They're only different by a shift, so essentially they have the same antiderivative, basically. So it's not, but yeah, we're going to do arc sine or arc tangent. Those are the ones we want. All right, so when I see that 1 plus x squared, that's what I think of. But it's not always arctangent. Okay? So, for example, what if this was only this? Is that arctangent? Well, why not? What's different about it? There's a 4 up there, not a 1. Well, wait a minute. What can we do with that 4? Just pull it out. We can just pull that 4 out, and then it's that. So it's just 4 arctangent, right? So if I have just a number up top, other than a 1, and I've got 1 plus something squared on the bottom, 1 plus x squared on the bottom, it's an arctangent. Okay, now, what if I had just an x up there? You can't pull the x out. You can only pull out a constant. So is this an arctangent? This is not an arctangent. So what's it got to be? Well, but what's the only other thing we know how to do? Use substitution, right? I mean, if it's not just a straight antiderivative from page 333, then the only other thing it can be right now, at least for the next 10 minutes, is use substitution. That's all it can be. So what could you let u equal? You could let u equal 1 plus x squared. Because what's the du going to be? 2x dx. And is that sitting right there? Well, the x dx is, right? The 2 we can deal with. So this is going to be a really good u substitution. A really good u substitution. Right? So this is not an arctangent. But I still think if you see a 1 plus x squared on the bottom, I think you should think, hey, this could be an arctangent. Right? But in this case, it wouldn't be. All right, well, now we got the problem in 41 where we've got both those things. We got a 4 and we got an x. What can we do there? Any ideas? We don't want to let u equal x plus 4. If we let u equal 1 plus x squared, then we get the 2x dx, which, but there's a plus 4 in there that's in the way. We got to do something else before we do a u.
Wait, split it in
Jazzy, say it loud.
Split
Split it apart. When you have a plus, now remember, you can't split the bottom, right? Single denominator, but if you have multiple terms on top, you can split it apart. So all we have to do, whoops, I forgot my dx. All we have to do is leave the denominator alone. So we can split this into x over 1 plus x squared plus 4 over 1 plus x squared. We just can't split the denominator. You can never split the denominator. But think about that. If you can add those back together because they have common denominator. Well, now we got the two situations we were just talking about. This one over here is simply going to be 4 arctan of x. Right? That's what that's going to be. And then this one, we're going to let u equal 1 plus x squared. We're going to let the du equal, or not let it, but that's what it will equal. The du will equal 2x dx. So here's another one of these little tricks, right? So next time you see something added on top, and whatever, that it might occur to you, oh yeah, I could split this apart. Doesn't mean you're going to every time, right? I mean, we had one, I know there's another one on there. Well, I'll show you in a minute here. Okay, so 2x dx, there's no 2 up there, so I'm going to divide it over. And I got x dx. So sure enough, there we go. There's my x dx right there. So that would be replaced with a 1/2 and a du. And then I got my bottom, which is my u, so I end up with 1 over u. Right? So everything subs out nicely. So what is that? ln? So that's 1/2. So my final answer is going to be 1/2 ln parentheses and then my 1 plus x squared. Oh, that's one of those where I don't, not parentheses, bars, absolute value bars. I don't really need the bars, they'll do it. Because 1 plus x squared will always be positive. But leave them there is fine. So there's my answer, plus my c. So there's an example of where we could split it apart. One of the integrals needed a u substitution. The other one was just a basic antiderivative. Okay? Now, there's a very similar one here. Number 43. Let's talk about this one real quick. 43 says, the top is 2x plus 3 over, what's the bottom? In parentheses, it's like x squared plus 3x. Am I reading that right? Plus 5 to the 4th power. So now again, now you look at this and you think, oh, that looks a lot like the one we just did. We could split it up. We could have a 2x leave on top plus 3 left on top. We don't want to do that, right? What do we want to do here? Let u be the, no, the inside of the bottom. Inside of the bottom. And again, if you're thinking 2 steps ahead, you got this, because you're going to say, well, if we let u be the inside of the bottom, x squared plus 3x plus 5, the derivative of that is 2x plus 3 dx, which the 2x plus 3 is setting right there. That didn't work on the last one. I'm not going to finish this one, but it's just a perfect u substitution. Ends up with a power rule, and then there you go. That didn't happen on this one. If you let u be the 1 plus x squared, you don't get x plus 4 dx, right? That plus 4 is in the way. It's an extra thing, and you can't just add it in there, right? You can't do that. So that's why we had to have a different strategy for that. So it looks very similar, but different strategy. All right. Another one? We can do one more. Trying to think. Yeah, more.
We do 37.
Let me see. Yeah, actually that was kind of what, that's what I was thinking of. Thank you. Good job. So what do you got? X squared over 1 plus x to the 6th dx, right? Okay, now, we just got done talking about how when you pick the u, and then you look at the du and see if it's setting right there. So what would be one option here of what to let u be? The bottom. The bottom would be that would be something that could come to mind. We've seen the inside a lot is what we look for. There's no real inside, but let it be the bottom. Now, actually, the bottom isn't inside. It's really the inside of an ln. That's what you do when you're letting u be the bottom. But so we could let u be the bottom. Good thought. But what about your second step? And let me ask it to you this way. What would you want to see on top if you were going to let u be the bottom?
Something
But so in this problem, what would you like to see on top if you were going to let u be the bottom? You'd like to see an x to the 5th, wouldn't you? See, what I'm trying to get you to see here is the things you're looking for to know what to do. When you look at that bottom and think, I could let u be the bottom, the very next thought that should occur to you is, but man, if I let that be the bottom, I need an x to the 5th up top. Now, we've talked about if you have extra x's, you know, what you can do. Maybe you can solve for x or something. But there is nothing you do if you need more x's, right? There's not enough x's. There isn't anything you can do, right? So we'd love to see an x to the 5th up there. Then this would be a simple u substitution. Okay, but it's not. So the next thing that would come to mind, some of you are already thinking of it. No, what can you split? Because you can't split the bottom.
X cubed.
This x to the sixth could be written as that. Now, I could do it the other way. That's fine, but I wouldn't want to do it the other way. I wouldn't want to do x squared cubed. I want to do this. Why?
Because when you do
Because now the bottom is 1 plus something squared, right? Anytime. So let's revise our earlier statement. Earlier I said when you see a 1 plus something squared, you think arctangent. You see a square root, a 1 minus something squared, you think arcsine. Well, now I'm telling you, if you see 1 plus any power, think of squared, because any power, you can make it a squared, right? Because power to power, you multiply. So as long as it's an even power, right, we can make it into something squared. And then, of course, the beauty of that is if you think of this as x cubed squared, now what do you talk about letting your u equal? The inside, which is x cubed, and then what's the du?
3x.
X squared, which is sitting there, and that's why this works so well. So add one more little tool to the toolbox, right? One more little trick up your sleeve. I don't know what other corny sayings can I come up with here. All right, so if I let u equal x cubed, du equals 3x squared dx, which is there except for that 3, so I'll divide it over. I've got x squared dx. So, new integral. The x squared dx is replaced with a 1/3 du. The bottom is now what? 1 plus u squared, because it's x cubed squared, and then there's nothing left on top, so we put a 1, and sure enough, that is an arctangent. So 1/3 arctan u, which we can just go ahead and put in place of the u, the x cubed, times, or not times, plus c. And again, this is a nice one to check real quick. If we were going to do this, if we were doing this as a derivative, 1/3 would hang out. The derivative of our tangent is 1 over 1 plus the inside squared. X cubed squared is x to the 6th times the derivative of the inside, which is 3x squared. Look at that. The 3's cancel. You end up with an x squared on top of 1 plus x to the 6th. Works out. Okay? So there is your answer. Okay? So, in other words, so any of those, so if you have a 1 plus x to the 8th, you have a 1 plus x to the 10th, right? That has the feel of an arctangent, right? Because it's 1 plus something squared. All right. So let's move on here so you have some time at the end, and then if you got some individual questions you want to ask, you can have a little bit of work time. So, vast majority, half or more of the gateway test, use substitution. It's an important technique because chain rule, it's about problems where there's something on the inside. Chain rule happens a lot. So it's an important word. Be some basic ones also. There's also going to be some for this new technique we're going to talk about right now. Okay? Now, this is called, so you might want to go to your notes, this is called integration by parts. Integration by parts. Now, there are other techniques. There's a technique called partial fractions. There's a technique called trig substitution. There's some other ones, and the names escape me right now. And those are later on in Calc 2. Typically, most college Calc 1 classes go all through derivatives, get into integrals a little bit of areas, a little bit of basic antiderivatives, whatever. But then it kind of depends. It depends on the course, depends on the instructor, what they do, what they don't do. For example, this one we're doing is not on the AP test, integration by parts. Okay? Won't be on our final, won't be in our package, but it's going to be on the gateway test. I just think it's the next most important one we need to do. But some books put it in different places. For example, the rest of the integral techniques are in Chapter 8 in our book. So this integration by parts is actually in Chapter 8. So our homework today, we're going to jump to Chapter 8 for one section. Okay? It's not harder or anything than anything else. It's just that's when they do the rest of these typically. Okay? Well, what it is, it's really the reverse of the product rule. Now, that doesn't mean that every one of these you do is going to be a product, although many of them are. But we've already done product ones that were use substitution. So it's not like it is with derivatives. You see a product, do the product. It's not that way with antiderivative, okay? We've already seen some products where we did U substitution. We did some quotients, like the one we just did was a quotient, and we did U substitution. So it's not, it's just not cut and dried rules like it is on derivatives. So anyway, but this one does come from the product rule. So I started out by writing the product rule out, right? We all remember that, hopefully. U and V are functions of x. They're multiplied together. The derivative with respect to x is u prime v plus uv prime. So what we want to do is that in reverse. So what I want to do is the antiderivative of both sides. So right now I'm going to do the antiderivative of both sides. Now what's the antiderivative of the left side? Just u times v, right? Just cancel out the derivative. And on the right side, I don't know. That's messy. So I'm just going to put an integral symbol and a dx at the end. And that's going to mean do the antiderivative with respect to x. So then we're going to have to mess with it here with some notation. Okay? So the antiderivative of the left side is just uv. And so, I don't know if you want to make a little note to yourself, but what we just did there is we did the antiderivative of both sides. Okay? Now, when we've been doing integrals, it has not been useful for us to use prime notation. What have we written instead of u prime? du over dx, right? And for v prime, it would be dv over dx. So my next line is just going to be doing that. Okay, now you're not, I mean, it's okay to write this down and see where this comes from, but what we're going to end up with at the end, we're going to end up with a formula that we can use. Okay, integration by parts is actually a formula you can use. Okay, the key is going to be recognizing when to use it. Well, for us, it'll be pretty easy. It's either going to be a basic antiderivative, or it's going to be a U substitution. And if it's not either one of those, which is the way I would attack it, since most of our problems are going to be U substitution, that's what I would try first. And as you'll see here in a few minutes, it's going to be pretty obvious that there's nothing to pick for U to substitute. So the only thing you have left is this. Right? It's harder when you get into Calc 2 and you learn 3 or 4 other techniques, and then you got to choose from. All right, so U prime is going to be this, V prime is going to be that. All right, now, since there's a plus sign here, I'm going to split this into 2 integrals. Okay? So my next page is to split that right side, just split it up into 2 integrals. Okay? Each one has a dx at the end. Right? So split it up into 2 integrals. Each one has a dx at the end. Now, look at that first integral. What does it look like you could do? Yes, you can. And also in the second integral. Cancel the dx. So all we've done here in these last 3 steps is we wrote out the product rule, then we did the antiderivative both sides with our integral symbol, and now it's just been notation. We've been just messing with the notation. And it looks like what we've ended up with is that right there. Now on this one I have the du in front of the v, so I want to move it to the end. That's where the du's, the dv's, the dx's, that's where those always go. So we end up with this statement right here. So now what I'm going to do is just subtract this one over to this side. Okay? So I now have uv minus the integral v du is equal to the integral of u dv. Okay? All right, now I'm going to flip that around. I'm just going to switch sides. I'm going to move this over to the left side, and I'm going to move this over to the right side. Okay? And that's going to give me my final formula right there. Okay, this is the formula for integration by parts. Now, the reason it's called integration by parts, I just realized I haven't updated my goals over there for quite some time.
Yeah, I have that every day.
What are you talking? Midterm. Let's see,
Yeah,
what was
that
that?
sounds like we're still doing.
2.5 weeks ago?
Yeah.
Oh, well, that's all right. Haven't had Nice thing is when the principals come in, they don't have any clue what I'm doing up here anyway, so don't tell them that, but you know, they look at it and say, oh, that's what, okay, all right.
But like the most complicated.
Yeah, just a big old thing up there, words. Alright, so. Now what does this mean? Why is it called integration by parts? Because here's what we're gonna do. The integral that we're given, now think about what u substitution was. We're given an integral, we don't know how to do it. It's not a basic antiderivative. So what u substitution does is turns it into another integral that we can do, that's simpler, right? That's what it does. Well, that's what this is gonna do too. That's what most of the techniques do, the integral techniques. They rewrite or turn the integral into another integral that we can do. Well, that's what this one is going to do as well. So we're going to take the integral we're given, and we're going to split it into these two parts. We're going to pick something in our integral for u, much like we do for u substitution. And then the dv is going to be whatever is left over. The leftover. So those are going to be, so we're going to split our, or not split our integral, but we're going to take our integral and we're going to pick it into parts, two parts. We're going to pick one part to be u, and whatever's left over is going to be the dv. Now, we're going to then take those and plug them in over here. So whatever I pick for the u is going to go right there. And then, how will I get du? Well, if I have u, what's du? The derivative of it, right? That's just like we've been doing. So once I pick my u, I'll do the derivative of it, and that'll be my du, and that'll go right there. Now, how will I get v? Well, my leftovers is going to be dv. How can I go from dv to v? Antiderivative. So to go from dv to v, you're going to have to do antiderivative. Now, what that means is our dv better be something we can just do an easy antiderivative. And generally it will. And it always will be in the ones I give you, right? So we'll want our dv to be something we can do the antiderivative of. That'll give us v, and then we'll put that in those two spots. And then hopefully what happens is my integral there is one that I can then easily do. So it's a little bit like u substitution that way. We're picking a u, and then but now we're plugging it into a formula, and then we're hopefully able to finish it from there. Okay? So it's different. But it has some similarities. Now, how are we going to know what to pick for u? Right? How are we going to know? Well, here's how. The dv is easy. That's just going to be the leftovers. Okay? Whatever's left over after we pick our u. How are we going to know what to pick for u? Well, here's the rule. Or not the rule, but a little acronym we're going to remember here. Now, some people don't believe in memorizing this acronym. They think you should just think it through, what's going to happen. So let's think it through first, then I'll give you the acronym. So we want to pick a u, and then the leftover is going to be the dv. Now the key is, what we pick for u is not a big deal because we're going to do the du, which is derivative. We do the derivative and. But the dv is the tricky part. So we should probably say, what should we pick for the dv, right? Well, basically what we're going to do is we're going to say, what do we want to pick for the dv, and then that'll be the last thing we want to pick for the u. That's kind of how we're going to do it. So the thing we want to be for the dv needs to be something we can easily do the antiderivative of. Now, what's the easiest function there is in the world to do the antiderivative of? Well, even easier than that.
Just a constant.
Even easier than that. E to the x. E to the x is the easiest thing there is to do the antiderivative because it's itself. I agree. X squared, those are pretty easy too. What about trig ones? Sine, cosine, those are easy too, right? The hard ones, the ones we don't have any rules for, are logs. We don't know the antiderivative of ln x, right? And we don't know the antiderivative of like arctangent or arcsine, the inverse trig, right? So logs and inverse trig, we would not want to be our dv. So guess what? Those are the first ones we want to choose for our u. So Liate stands for log, like ln x. And the L stands for log, the I stands for inverse trig. So if we see a log or an inverse trig in our problem, we want to pick that for our u. So that's what Liate is first choices for what to pick for u. A is algebra because that's just kind of in between. X squared, x cubed, they're easy to do derivative, they're easy to do antiderivative. We could go either way with those. And then the trig, T is for trig, like your sine and cosine. Those are easy to do derivative, but they're pretty easy to do antiderivative on also. And then E is for your exponential, like e to the x. Those are really easy to do antiderivative on, so those would be the last thing we'd want to pick for you, because we're going to do the derivative on those. All right, so when you, and now this kind of tells you right here, something you might put in your notes for integration by parts. A lot of times an integration by parts is a problem that has a mixture of function families. Not always, but it's just one little thing to look for. Integration by parts a lot of times has a mixture, like it has an algebra with a trig, or an exponential with a log, or a, whatever. It's kind of got a mixture. If you look at in your homework in the book, 23 through 50, those first group, they were all like algebra ones. They had x's in them and powers. And then you had a group that had mostly just trig functions in, and that kind of stuff. So sometimes that's a hint that those are used substitutions. Not always, but it can be. All right. But the big thing for you, I think, is going to be, I can't do anything else. There's no use substitution. It's not a basic antiderivative. I have no choice. I've got to use this new thing. Now, I told you, there's only going to be a couple in the gateway test. If you're using this, the thing I hate is spend all this time doing use substitution, and we get to the gateway test, and people start using this thing. If you're using this more than twice on the gateway test, you're using it too much. Okay? You're not going to be that many on it. Okay? Most of them are going to be to use substitution.
Could you use this, like technically, instead of use substitution?
No, this isn't a choice. Right. This is not a choice. This is not, I think I like this better. I'm going to do integration by parts in this one. No, that's not what it is. Now, there are some where, and we'll get into some, not today probably, but there are some where you start with integration by parts, and then as you're working it, you got to do a use substitution. Or there are some where you start with a use substitution. Remember, because what do these techniques do? They give you a different integral. They turn your integral into another integral that you can do. Well, sometimes you can do a use substitution, it turns it into another integral, and that integral needs integration by parts. Or vice versa. Okay, so that's a possibility. All right, let's take a look at this situation right here. So let's do a couple of them together. So this first one, so what I've done here is I put two on the same page because they look a lot alike. Right? They're very similar. Now, the first one is one like we've been doing. The first one has what in it? The first one is going to be what method?
Use substitution.
Because you can let u equal what? Right? And so this is part of this recognition thing that you need to be getting comfortable with. You need to look at one like that and say, aha, there's an inside. It's x squared. I can let u be the x squared. The du is 2x dx. There's an x dx setting right there. Beautiful. That's what I want. That's going to work. Use substitution. So that's what I want to do. So you let u equal x squared. The du is 2x dx. There's no 2 in here, so I'm going to divide that 2 over. I got x dx here. So now I sub. My x dx would replace with a 1/2 du. This would be what? This is just e to the u. Right? The antiderivative of e to the u is e to the u. So this just becomes 1/2 e to the u. U, of course, was x squared plus c. And we're done. Okay? So these two on this page look very similar, but they're very, very different. Okay? Use substitution needs, right, to have a specific thing happen. You need to be able to pick a u so that the du is setting right there. Right? Or some version of that du is setting right there so things sum out nicely. That's what you're looking for. So you look at this one, and what's the only thing you could even think to pick for x, probably? E to the x could be one thing, or what people usually say is x, let u equal x. But we talked about that earlier, right? You would never let u equal x in use substitution because then you just get the same thing you had with different letters. So you wouldn't let u equal x. So the only thing you can even remotely think to do is let u equal e to the x. The problem is, think about this now. You get du equals e to the x dx. So you can sub that out, but you have this extra x. Oh, well, what did we say to do if you have an extra x? Solve for x. Well, the problem is when you solve this for x, you're going to get like a log, and then you're going to end up with an ln in there, right? Which is not something we know how to do the antiderivative. So it's not going to end up getting you anywhere. So you're going to go down that road, you're going to get stuck. Well, that's when you would say, well, the only other thing we have is integration by parts. So let's do integration by parts. Okay? Now, hopefully you recognize that earlier. Now, after doing a few of these, you're going to start to notice that they look pretty simplistic. They don't have all this inside stuff. Well, that's because U substitution works when you have a bunch of inside stuff. When they look complicated. That's when U substitution works its best. So when you get these kind of simplistic looking ones without a lot of powers, without a lot of inside stuff or any inside stuff, that's when you think integration by parts. All right, so we got an algebra and we got an exponential. Which one do we want to pick for our U? The algebra. Liate. A, algebra, comes before E, exponential. Okay, so we're going to let U equal x. Well, that's weird. I just got to say you don't let U equal x. Well, in this you can't, right? Not in U substitution, but in this you often do. All right, and then here's how I would write it if I was you. I would just go off to the side for my b's over here. So I got U equal x here, and my dv would be all the leftovers. So that would be what? E to the x dx. Don't forget the dx. Okay? Now, if u is equal to x, what's du? 1 dx. So let's just put dx. Now, don't forget. Now, the hard part about this, one of the things about this is in the middle of this problem, you're doing both derivative and you're doing antiderivative. Because how are we going to go from dv to v? Do antiderivative. So we do the antiderivative v to the x. Now, we don't have to put the plus c on. Sometimes people say, what happened to the dx? Well, what do you mean what happened to the dx? It's just like doing this reverse. You had this, which didn't have a dx. We did the derivative. It showed up. Here, we're going in reverse, right? So the dx just goes away as we do the antiderivative. Okay. Now, don't put it on there. We'll put it on at the end. We'll put the plus c on at the end. Okay, now what we have to do is just put into our formula. So our formula is uv, so you just have to memorize this, minus the integral of v du. So just put it on note card, say it to yourself 100 times. uv minus the integral v du. uv minus the integral v du. Okay? All right. So we're just going to plug stuff into it now. So we put our u times our v, so that's x e to the x, minus the integral of v, which is e to the x, du, which is dx. And of course, this is what we wanted to happen. We've now created a new integral that's an easy one to do. And so our answer is x e to the x minus antiderivative e to the x is e to the x plus c. And we could test that. We could do the derivative of that, do a product rule, blah, 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 and it would work. And we would end up with that. That is called integration by parts. Now, there are a couple little things that can happen, so I want to spend just a few minutes here looking at some situations that may come up. We're going to keep them fairly simple for the gateway test. There might be a few in the homework that get a little interesting, and we, give them a try, spend a little time on them, but it'll help you get through the process. But the ones on the gateway test will stay relatively simplistic. So let's look at this one. So again, there's a mixture of kind of a function family there, a log with an algebra. But again, the first thing you would think, is there anything in the world I can pick for my u? There's really no inside. Now, think about the inside. The only inside there's the log. What would be great to have inside the log for this to be a nice u substitution? Good. If there's an x cubed inside that log, this would be a great u substitution problem. Because the x squared du is setting right out there, and there you go. But it's not, so that makes you think this must be an integration by parts. So Liate would tell us u is the log. L, Liate, first choice always for a u is if you have a log. So the dv this time would be the x squared and the dx, the leftover. So du is 1 over x dx, and the v is 1/3 x cubed. Very good. We got to remember that we're doing antiderivative then. Antiderivative on that one when we go from dv to v. So we put it together. The formula, remember, uv minus the integral of v du. So I would put the 1/3 x cubed in front of the ln. Doesn't really matter, but just looks nicer. Minus the integral of, now here's where what can happen. Last one was about the easiest one you could get on integration by parts, quite honestly. When you get into this integral v du, sometimes you have a little bit of a mess and you have some simplifying, and that's kind of what we have here. We got 1/3 x cubed times 1 over x. If you want to do that work off to the side, that's fine. But what happens there? The 1/3 could go out in front, and the x will cancel, and it ends up being x squared dx, right? So my final answer, you don't want to forget this stuff over here to the left. Sometimes you get caught up in this integral and you forget about it. Minus, and what will we have? We'll raise that up to a 3. Divide by 3, so we'll have another 1/3. So that's 1/9, not 1/6, but 1/9. X to the 3rd, and then you can stick your plus c on at the end. Okay? Now, if this would have been a definite integral with numbers in there from 2 to 3, you do everything the same all the way to the very end. Remember in u substitution we talked about how you could change the numbers into u's? Well, we don't ever get our integrals to have u's in them here, right? We always go to x's. We put our u's and dv's and stuff down, but then we plug them into the formula. So we always have x's. So what you would do on the integration by parts, if it was a definite integral, is you just get all the way down to the bottom here. Instead of putting on the plus c, you do your right bracket, put your 2 and your 3, and then subtract. F of b minus f of a. Put in a 3, put in a 2, and subtract. Okay? So that would just come at the very end. So you do everything the same until you got there. All right. Let's do one more. Let's see, I'm going to skip this one. I'll just make one comment about this one. There's only one thing said. It's an inverse trig. Now, according to Liate, that's pretty high on our list of things to pick for a u, right? So on this one, I'll just write this down, and then you can finish it if you want later. But this is one where the dv, the leftover, is just dx, right? And then the du, what's the derivative of arctangent? 1 over 1 plus x squared dx. What's the antiderivative? Well, this is a 1, so the antiderivative would be x. Okay, now, when you go to put this together, this is a little bit like what I was talking about earlier. Well, it's not a little bit, it's exactly. So when we take u times v, that'd be x arctan x minus the integral of v du. Well, if you take x times this fraction, wouldn't that just put an x on top?
Yeah.
Wouldn't it just be that? Does that look familiar? Can you just do a straight antiderivative on that?
No.
No, you have to do what?
The u substitution.
This was the one we did with u substitution. You might think arctangent's got an x here. This is the one where we let u be this down here. The du is 2x dx, which is same right there. So that's what I was saying earlier. Sometimes you start as an integration by parts. What you do is trade it for another integral. Sometimes that integral needs a u substitution or some other technique. And here's an example of one where that happens. Okay? So that's what you would do to finish. You would pick your u was the bottom and go from there. Now, the same problem, you have two different u's, but it shouldn't be confusing. Okay? Because you're already done with those ones up top. All right, so that's what I was getting at when I said sometimes then you have to do something extra with that. All right, one last thing. This might happen one time in the homework. It's not going to happen on the gateway test, I promise. This looks a lot like the very first one we did. It's got an algebra and it's got an exponential, right? So what are you going to pick for the u? Algebra. Liate algebra comes before exponential. So you're going to pick u to be the x squared, dv's what's left, which is e to the x dx. Difference is the first one we did had just an x there, not an x squared. That was the difference. Okay, and I'll show you the main reason I want to show you this problem. So the du is 2x dx. And the v over here, antiderivative of that is e to the x. Okay, so uv minus integral of v du. So u times v would be x squared e to the x minus the integral. Now, hang on here a second. This is something that didn't come up in any of the other problems, and I remember seeing this past year, so I want to point this out. This 2 right here. When we do u substitution, what usually do we do with it? We usually divide it over here, because it's not in the problem. Are you going to do that here? You are not. It was funny, in the other class I talked about this, like 3 people all got their erasers out and started erasing, because they'd already done it. When they wrote down this, they divided the 2 over. We don't want to do that, because in our formula, we want v du. We want to put whatever du is. We want du equals. We don't want anything else over here with it. Whatever du equals is what we want to put in there. So when I do my v, which is e to the x, and then I do my du, I'll put the 2 there, maybe the x there, doesn't matter, dx there, kind of rearranging it, but it's v du. So that 2's there. We don't want to divide that over. Okay. Uh-oh, now what do you notice here? Well, it's not quite the same thing. It's x to the first, but it's another integration by parts. Well, that's because we started with an x squared. And that took us down to an x, and now we got that. What if this would have been x to the 6th? Yeah, you'd have to do it like 6 times. Because it went down to x to the 5th, x to the 4th, x to the 3rd. You're not going to have to do it. Not going to make you do it. Sort of. You'd sort of see a pattern probably. But anyway, so you'd have to do another integration by parts of that. But the lesson of these last 2 is you're trading one integral for another that you hopefully do, and you might have to use a different technique, or in this case, the same technique you get. Gateway test, you won't have to do that. One time only, you'll be able to get the integration by parts. It'll go. Okay, it'll work. All right, so for homework here, let's do, I think on your assignment sheet there, it's got 8.1, and it's got, I think it's numbers 9 through 11. I lost my assignment sheet here somewhere. I think it says 9 through 11, 15 through 20, and 31. Now, 15 through 20, some of those are those definite integrals. So like I said, when you go to the, you just work it all the way out to the end. Instead of putting a plus c at the end, you put your right bracket, put your numbers in to do that. And then I've got another small little LH packet here with some u substitution. So this is parts. 8.1 is parts, and this here is u substitution. So there's a line right below the bold, the first time on your assignment sheet where it says LH page 310. Let's do that line there. 7, 9, 16, 19, 24, 35, 37, 43, 48. So that's about, what is that, about 9 problems and another, that's about 15 problems. So that would be pretty good practice right there. Okay? So here is that packet.
Mr. Clark, did you maybe put 48 twice?
Maybe not. I would say you do it twice.
Double check your
Do it wrong the first time and then fix it and do it right. Actually, there's not a 48 anywhere in there. That is supposed to. Well, I got one number correct in each of them. This one was supposed to be 43, and this one was supposed to be 58. So, what's that far off? Like 50%. Which is passing if it was the AP test. See, so of course writing two-digit numbers is not quite like taking the AP test. Yeah, I'll have to count it right, won't I? Can't argue with you. I would say I would deny it, but I'm still recording, so I think you do have it on record.
Yeah.
Like how we schedule like other days.